All right, very good. So on that foundation, we can move into a pretty interesting application of the benefits of modeling and optimizing a production system, showing the power of this using the 5 levers that Roberto mentioned. So we have 2 speakers. Garrett Bryan, who's an implementation leader at Strategic Project Solutions. Garrett is responsible for the configuration and deployment of PPM solutions in the energy and industry sectors. He has 10 years of experience. He knows how to do this stuff. Shubhanil Mitra is an associate partner at McKinsey and a part of their CapEx and sustainability practice in Southeast Asia. He has decades of experience working across the energy and material sector, especially across EPC, oil and gas, rail, and power clients. And he has a particular focus on cleaner technologies like hydrogen and EV. So I'm going to turn it over to you both now and let you take it away.
Thanks, Gary. All right, hey everyone, I'm Garrett with SPS. In this presentation, we will talk about modeling and optimizing production systems and what can be achieved. And we'll look at that on actual deployment scenarios. So we have a lot of information to go through in 20 minutes, and I'm going to hand off to Shubhanil from time to time. So working for SPS for the past decade, every customer has come to us with a problem. The project's in need of help, schedule is delayed, they're way over budget, and more often than not, their efforts to recover did not meet expectation. At the end of the day, the developed and predicted schedule was not reliable, and the actual performance always fell short. So the question is, can we create a reliable and predictable outcome? The answer is yes. Yes, we can. We can create predictable outcome, and we can create one that is reliable. Together with McKinsey, we were able to help a customer achieve 20% schedule acceleration and 300% improvement in cycle times. Now, that's twice as effective as the projected classical lean applications for the same effort. We did this by mapping the production systems for the construction projects and optimizing their performance using the PPM methodology. The projects we worked on were a 14-kilometer toll road and a port for large ships. Both were infrastructure expansions in Indonesia. Now, before we get into the results of these projects, we need to understand what a production system is and what we can do with it. So we've seen this slide already, but it's very powerful. Simply put, a production system is the series of steps that transforms units from an input to a desired output or product. To think of this in construction terms, we can use an example of transforming raw concrete into a usable dock and all the steps necessary to make that happen. The configuration of the system itself will determine how fast units move through it. This is the throughput, and the bottlenecks in the system prevent throughput from meeting the demand. If demand is not met, then the schedule suffers, goals aren't met, and your budget goes out the window. To make sure this doesn't happen, we need to optimize the production system itself. And to do this, we map the system that the project uses to build the final product. We don't create the production systems, they already exist. Construction uses it to transform the product. Every project can be defined as a series of systems that, when they operate together, achieve the desired results. Once they're mapped, we can begin to understand how the production systems themselves work. Now, operation science, which we don't need to get into, defines the rules for the production systems and how they operate. And it doesn't matter what we build, offshore platforms, data centers, even manufacturing cars. The processes used are the production systems, and they all follow the same rules. They can be mapped and they can be optimized. Where optimizing and modeling comes into play is what we do once we map it out. With the systems mapped, the rules in place, we can optimize using 2 methods: analytical modeling and discrete event simulation. Now, analytical modeling is a microscopic analysis of the components in a target production system. Think unit of production. This is used to determine the optimal configuration in order to meet the demand. Discrete event simulation, on the other hand, allows the production system or any number of cooperating systems to simulate the result. It uses the allocation of capacity, equipment, labor, resources to move units through the system. By manipulating the components of the systems in either approach, we can create an optimal, reliable, and desired result that can be predicted. Now, Shubhanil, I'm going to hand off to you to introduce us on our first project.
Sure, thanks for that, Garrett. So the first project, I'm going to give you a little bit of an overview. This was a toll road project, and there was a specific challenge in a particular section of the toll road project. As you can see from the picture, it's a low-lying marshy area, and there was a section of the bridge that had delay issues and which was in the critical path. And for every day of delay, what it meant for the client was lost revenue, and there were also challenges of liquidated damages. So what did we do? We took the analytical model approach. So essentially in the analytical model approach, we can go to the next slide, Garrett. So in the analytical model approach, essentially we analyze existing production systems, which were essentially precast piles, sheet piles, pile caps, pier heads, and columns. And we try to model that and determine how we should balance other resources or how we should apply lean techniques or techniques that have been suggested by the system to accelerate the production in the activity. And here, if I recall correctly, we took a two-pronged approach. First, we took the classical traditional lean approach. So we went to the site, we saw what could be done to accelerate the program. And then we also had help from the SPS team to model and come up with more advanced recommendations on how to speed up the entire construction process. If we go to the next slide, you will see that on a net basis, we were able to improve the overall cycle time of these production systems by 300%. And 100% of this improvement was over and above traditional lean techniques, right? So that is the power of applying the SPS PPM solution, where you can combine some of your traditional lean thinking and certain advanced concepts in PPM to get the best output for accelerating your projects. Sure. Okay, Garrett, I'll hand over to you to take people to the details.
Yeah, thanks, Shu. So the analytical model allows us to see how manipulating components of the production system will change the throughput. Not only does it show the results, the analysis will tell us specifically where to focus in order to optimize. The results were translated here into schedule impact, which is what we were trying to address on this particular project. To minimize the impact, the opportunities were revealed as shown here, and this was the optimal strategy. And it's built from optimizing or analyzing the current strategy. By mapping the production systems as they existed, we have the 5 production systems here. We translated these results into schedule impact for the current strategy. And this gave the project team insight on where we should focus. And if we keep doing what we're doing, this is where we're headed. Now, focusing on these bottlenecks allowed the team to quickly and effectively optimize their process. And how we did this was by focusing on the components of the production systems themselves. The capacity for units to move through a production system is determined by many factors, including allocation of resources. The analytical model reveals how the resources are being utilized in the production system and highlights where they're overused. This creates a bottleneck, as seen here in the orange. It's important to understand that production systems are not always intuitive, and increasing the amount of resources to alleviate bottlenecks may place higher burden on other resources, and this will create bottlenecks that may not have been apparent. Now, WIP, on the other hand, affects throughput in a very defined manner, and this can bring a production system to a grinding halt if it's not managed effectively. Too many units in the system. If we're putting too much work out there, the cycle time goes through the roof. And if we don't work on enough items, then the demand's not going to be met and we're going to miss the target dates. The analytical model tells us the exact WIP we need to meet the demand. Now, WIP and capacity aren't the only options available. I'm sure many of us have been exposed to the 5 levers. By the time McKinsey and SPS came to this project, the product design was already determined, and changes to the design would have significantly impacted cost and schedule. However, the other components were leveraged to meet the demand, or in this case, minimize the schedule impact. This is what we saw in the targeted production systems, and by leveraging what was available to the construction team, we were able to achieve massively reduced cycle times. Now, Shub, I'll hand back to you to introduce the next one.
So this was the second project that we did and applied PPM. This was a harbor project, and this was also delayed. And this was way more complex than the toll road project that we did, simply because the toll road was an analysis of one production system, the piling. However, this was a combination of multiple production systems that were interfacing and handing off to each other. And there were 3 separate milestones and workload allocation across 3 parallel work streams that we had to look at. So it was way more complex from that perspective. And the challenge for the client was that one of these milestones was actually tied to some penalties. And if the client would miss that specific milestone, they would incur a certain amount of penalty. So that was the problem statement. And to solve this, we applied the discrete event simulation. I will talk a little bit through it on the next page. Here, you would see that the model is way bigger and way more complex, and there's a lot more interfacing and handing over. It's basically the digital twin of the dock construction production system, right? And it differs from the analytical model due to a complete series of production systems and hands-off. After doing this modeling, I think the results were quite impressive and something that the client took away to actually meet their schedules and their deadlines. So on the next page, we have the results where we were able to accelerate the schedule by around 20%, specifically for that one particular work stream that was tied to certain penalties. And overall, we also did a cost benefit analysis because increasing resources would incur some cost, but then it would be traded off against the penalty that the client would incur if they missed the milestone, right? And I think overall, there was a net benefit of $1 million or so by avoiding the penalty. And then Garrett will take you through the further details of the technical analysis. Yeah.
Sure, thanks, Shub. So just like the analytical model, to optimize the system using discrete event simulation, we had to analyze the current strategy. If the team kept doing what they were doing, where were they going to finish? And from there, we quickly manipulated the levers and achieved the desired outcome. Not only can we achieve the desired outcome, which was the case with finishing on time here, we can optimize for other aspects such as cost. And what happened on this project specifically, once we ran the analysis and determined that we could meet the milestones, in some cases, we actually beat the milestones, and the customer wanted to know, okay, what's the least amount of cost we can use? If we meet our target milestone, I believe it was a political one, the G20 summit, then we don't need to use all the resources for the remainder of the project. So we had an optimized strategy to meet the initial demand, and then the remaining project completion, we streamlined and made the resource utilization efficient. Sure, we could have ramped up and finished the whole thing in a month, but the cost would have been way too much. So what we did was we simulated every strategy. And we ran something like north of 32,000 simulations. And by doing this, we found the optimal configuration for both time, cost, and demand, and sticking to the levers we could control. Again, we didn't change the actual product. Now, discrete event simulation allows this holistic approach based on the simulated outcomes. And it does this by allowing us to dissect the results and see how the inventory specifically moves through the systems and how the resources are allocated for capacity in response to demand. As Shub said, this is the digital twin of the construction project. So there's many production systems that all tie together for each unit to create the outcome. So as the simulation runs, each production system tells a story. By testing the amount of configurations that we did, we found numerous bottlenecks, all in different areas. And we found where alleviating one bottleneck created further bottlenecks down the road. And one of the examples was the decision to reduce the cure time for concrete. Originally, it was a 7-day cure time, and the team wanted to know if we used 3-day cure time, which would reduce the wait time, how would that affect the system? And what it did was it introduced too much WIP down the line. If we finished the concrete slabs quicker, the outcome became worse because too much inventory was sitting on site and there wasn't enough capacity to manage the introduced WIP. So understanding how the production system operates for the entire project allowed us to provide the customer with achievable and predictable results through rigorous analysis. Now, the discrete event simulation gives all the details on how resources are allocated in response to demand. This is critical to show where the bottlenecks exist due to overutilization and where underutilized resources are being wasted. Further simulation revealed where increasing one resource did place further burden on another. The example here is actually a crane. There was a bottleneck where the crane was being overutilized, so we added more cranes, and what that ended up doing was placing more burden on the rebar team further down the road, and they couldn't keep up. So again, you had a problem with WIP entering the system, and the whole production system came to a halt. And this proved through rigorous analysis that adding more resources did not create higher throughput. And finally, probably the most valuable is where discrete event simulation shows us how to analyze variability. Production systems are affected by variability, whether we like it or not, and there's no way to eliminate it. We can't control the weather. However, we can minimize the impact of variability on the system. The DES allows us to do this by running the simulation multiple times, which provides a distribution of the results. High variability yields a wide dispersed outcome, where when we reduce it, it gives us a more concentrated, more predictable result. And the example on the project was when we ran the simulation for the faster cure time, the variability increased because of the WIP that entered the system. The distribution was far more unpredictable than when we used the longer cure time, which was a more controlled process. Now, this is a useful approach when trying to achieve an acceptable level of outcome. Now, these deployments were valuable to the customer. Saving time and money usually is. But not only were these results valuable, the fact that we ran these analysis and showed these results and did the application, we didn't touch construction in the process. And this made it a far easier approach to adopt. And couple that with the fact that these were conducted remotely, it allowed a quick turnaround for analyzing and testing various strategies that the customer found useful. While visiting the project, if I had gone out there to Indonesia, getting firsthand knowledge does improve data accuracy, and that's always an option. But what we did achieve from a distance is certainly worth investing in. Now, it's important to understand that no matter the project, no matter the strategy, the results can be predicted, can be improved, and can be made more reliable. Now, that was a lot of a lot of information to go through in 20 minutes. So I'm curious to know what questions are out there.
Well, you got your lit the wires up there, guys. That was excellent. Let's start with this question. I think it's really good. How do you get valid input data for simulation capacities, durations, statistical distributions?
So the process we use includes a step for validating, and we can do it once if the data we get is very accurate. We have our validation process, and we translate it into something that we go into the analysis. And if everybody agrees, if the customer agrees, and we use the experts, we will talk to construction directly if we need to. If everybody says, yeah, that looks good, we get the green light and we go through the analysis and see the result. Most often that doesn't happen. It's a back and forth many times, but because we do this remotely and sometimes we do go on site, we can do that multiple times in a day if needed.
Yeah. And one more thing to add over here, I think these were projects which were already ongoing. It wasn't like pre-construction. So there was some baseline data available on what was happening then and there in the present, right? And we got those inputs from the supervisors and the construction guys on the ground.
All right. Another question. How do you build a production system if the outcome are customized and bundled in batches?
So the batching is important in the production system, but we aren't actually creating the production system. It exists on site. We are just building the digital twin of what's actually going on. If the project is working in batches, then we will model that. If there's a single piece flow, then we model that. Whatever the current scenario is on site, we're just capturing that and building the simulation.
All right. Garrett, probably for you, we're not here to promote software, but the question is, what software do you use? Can you also analyze flows with recycles and multiple inputs and outputs?
Yeah, in the case, let me go back to multiple inputs and outputs. This version here is a series of production systems with many inputs, many outputs, and many sources of demand. Now, discrete event simulation, we haven't created that. That's something that already existed. The software we use, though, is very effective because it is built using the operations science framework, all the underlying principles and rules that production systems follow. We can leverage those in our analysis. So it's very geared towards construction and is very effective.
Which is an SPS application. So another question for you. In the harbor example, it looks like the team took the recommendations. What was their initial response to your recommendations?
Well, where is that slide? So after we validate, we have the initial analysis, which is the current model. So the current strategy, and the orange here is we ran 100 simulations for the current strategy. It gives us a distribution. And we tell them, okay, because of variability, it's gonna be a distribution on a timeline. How confident do you want to be in your answer? 100%, 90%? So the team said, we want 90% confidence. We're fine with that. And on a distribution curve, you always have outliers. So the orange there shows you the 100%. The black bar gives you the 90%. That gave us our acceptable level. And the current strategy fell in line with the classic predictable results. What project controls was forecasting, this model fit that outcome. And by having that agreement between the two methods, the customer was confident that, okay, we have a simulation that actually does reflect what is happening on site because we're using actual data to feed it.
Yeah, and specifically, I guess what the client liked was the variability modeling, because the client was using some of the softwares like MS Projects and all before. But I think one of the biggest challenges is the variability model is not there, right? Yeah, exactly. So this was very insightful for the client. And to be able to do this gives them a much more improved confidence on what would be the end of project time that they could predict.
Okay. Well, we still got a couple more questions, so we can move through them quickly. Your prescriptive analysis tool is simulation. What about neural networks, other heuristics like GA or simulated annealing in terms of accuracy?
Oh man, neural networks. So I've had some training in neural networks, and the problem with neural networks is the outcome is only as accurate as the data that's feeding it. And when we are trying, we can use norms, but production systems are like engines, and each one is slightly different. Where a neural network would really benefit here is gathering data quickly and turning it into something that we can actually use. But it would not be effective, not yet, in actually creating an analysis and predicting the outcome. Operation science already does that for us. We're just solving an equation, and we don't need a neural network to do that.
Good point. One more quick one. During delivery, would you propose using this in parallel to a typical schedule?
Oh, yeah, absolutely. The question on what's the difference between a schedule and a production system, I always fall back to an analogy. If I'm driving a car and I'm going from point A to point B, the schedule tells me where I should be along the journey and how much gas I should use. But if along the way the engine starts sputtering and doesn't work, I don't just put my foot on the floor and hope for the best. I have to diagnose the problem. So the schedule gives you a very good piece of information and tells you where you should be. The production system and the analysis we have here is a great diagnosis on where the problems potentially will occur and can we actually meet our schedule.
Excellent. Excellent answer. And with that, we're going to have to wrap this one up. This was really meaty. Excellent presentation. Thank you. Thank you both for sharing your experience with us.